And now we move on to chapter 4, talking about atoms and elements. And let's look at this picture here. And you can see a person there with a dog on the beach. And so you can see there are things like hydrogen and oxygen, and there's that molecule there, trimethylamine. So that molecule is part of the fishy smell that happens there at the beach. So it depends on where you're at on the ocean. And that rock there has the structure, the silicon dioxide structure that's typical to quartz, where a lot of the continental crusts are made of silicates like quartz, here on Earth at least. And so, oh yeah, the other molecules are oxygen and nitrogen as well. So I'm assuming the blue is nitrogen and the red is oxygen based on the other things. So it depends on where you're at. So I mean, I'm recording this video in Hawaii, and we don't have silicate sand beaches. We tend to have carbonate sand beaches. We have a bunch of different types of beaches actually, but primarily it's carbonate sand. I mean, although that's not really a beach where this person is at, it's a rock. So there is some variation in that. So just be careful about blanket statements when you say things. Probably because 70% of the United States lives east of the Mississippi River, and that's probably the primary target audience of this. But the point of this is to look at the atoms. So looking at the atoms here, and they form together to have stable units known as molecules, and since that's the primary component of matter that we interact with, that is very important to us. So atoms are really, really tiny, very, very tiny, and eventually we're going to talk about a mole, and we have a huge number that we talk about how we can relate atoms to. But to give you an idea, if every atoms in a small pebble were size of the pebble itself, this pebble will be larger than Mount Everest, and Mount Everest is the tallest mountain in terms of altitude in the world right now. So more things. So atoms compose matter, at least the matter that matters to us. I mean, there's other forms of matter that are not atomic, but they are typically considered more exotic. And the properties of these atoms determine the properties of the matter, specifically the electrons and the interactions with the electrons. And we'll talk about more about that. Aforementioned in other chapters, the smallest unit of a element is an atom. So if you break apart an atom, it no longer becomes an element. And we know of about 91 different elements. This is a debatable statement. So it just depends on what you consider to be man-made and nature-made. And there are various processes that might happen that we can form elements. We know of, at the time of this recording, 118 elements. And it's not entirely sure if we will discover more. We might. We're not sure. There's 118 elements as of the recording of this video. And so we don't know, and maybe we can find them. Many of these are very, very small. So and that's what I mean by the debatable nature of the 91 being naturally occurring. So it's like a more or less chemistry can be at this level can be considered to be very objective, but some things are subjective, and this is one of the things that are subjective about this class. So let's go through a little history of this. So Democritus and his mentor Leucippus were the first to theorize, and they're Greek, these are Greek, that matter is made of very tiny spheres, and they called them atomos, or atoms, meaning indivisible or indestructible. So you cannot break matter down into smaller parts. Of course, the Greeks only thought there were 4 elements: earth, wind, fire, water. Then moving on, Dalton came and came up with his atomic theory. And although atomic theory is very well understood and accepted, it used to not always be this way. People were arguing about the state of atomic matter, if that's real or not, for a very long time. So here's the bases for atomic theory. Each element is made of tiny indestructible particles called atoms. This is mostly correct. They're not indestructible. All atoms of a given element have the same mass that distinguishes them from other atoms. From other elements. This is kind of true. We'll learn about isotopes later. This is mostly true. Atoms combine in simple whole number ratios to form compounds. Now, okay, finally we got something that's true. This is absolutely true in Dalton's atomic theory. 1 and 2 are mostly correct, but not entirely correct. So, of course, there is not really any question of whether or not atomic theory is valid or not. We can image them using scanning tellurium microscopes, and here is an example of making a boy in his atom in the made by IBM. So then comes along Thomson, and Thomson played around and found a particle that's part of atoms called electrons. So, well, the point of this is that this has broken Dalton's atomic theory because he was able to break apart atoms. So, and Thomson said, well, electrons are negatively charged. They're very lighter. They're much smaller and much lighter than atoms. And they are uniformly present. And then there must be a positive charge. Well, he inferred from this, if electrons are negative, there must be a positive charge inside the atom to counteract that. And then this moved on to the plum pudding model. And maybe a more American, if you are an American watching this, probably a better way to think of this model would be like a blueberry muffin model. So imagine a big blueberry muffin where the blueberry muffin itself is the atom, and then the blueberries in the blueberry muffin are the electrons. So of course the blueberry muffin is it's a 3D shape. Maybe think of a chocolate chip cookie model. So think of the cookie as the entire atom, and then the chocolate chips as the electrons. So the idea is that an atom is this region of positive charge, and then electrons are floating around inside the atom, and they're smaller. So that's the idea. This is the plum pudding model, and you can see with this, atoms are not. They're basically big blobs. So there's not structure to it. So you have Dalton that has atoms being spheres, and you have the plum pudding model. It says that atoms are just kind of this area of positive charge. So now Rutherford came along and says, you know what, I'm going to figure out this. I'm going to figure out once and for all which model is right, if it's the plum pudding model or if Dalton was right. And so Rutherford went and took a piece of gold. You can hammer gold really, really thin, and then took an alpha source and alpha particle source, and combine and put it into a block of lead with a little hole out, so it was shooting alpha particles out. And alpha particles, they're heavy. They're basically helium nuclei, so 4 atomic mass units, which essentially are about 8,000 times as massive as an electron. So you can see that if an alpha particle hits an electron, it's just gonna knock it out. So what Rutherford was hoping was, with this experiment, was to say, all right, so if the alpha particles all scatter, then we'll verify Dalton, and if the alpha particles just go straight through, then that means the plum pudding model is right. So Rutherford did this and then put a phosphor screen around it, and some poor grad student had to sit around with a clicker and sit at certain angles and count how many times there was a flash of light, and did it all the way around the circumference of this detector, compiled all the data, and took it to Rutherford. Rutherford looked at it and was like, this isn't right. So what did they find out? Well, most of the particles went straight through, and but some of them were deflected at an angle. And like this of course means that neither Dalton's atomic theory is correct, and also the plum pudding model is wrong. So how could this possibly be the case? So Rutherford made the grad student do it again, and grad student went and dutifully did all this, and then made the data, made it all nice and neat, gave it to Rutherford. Rutherford said, "You're still wrong. What's wrong with you? Do it again." The grad student's like, "Hey, look, I've been in the lab, in the dark, looking at this phosphorus screen, flashing the clicker. I've compiled the data. I've done it twice. I've got the same response. This is right. If you don't believe me, you go do it yourself." I mean, of course, this is not quoting directly. This is kind of, I'm kind of doing the abbreviated history of this. And then Rutherford sat down and said, "Maybe this is correct." And then Rutherford thought some more. And then this is what Rutherford thought. So he thought maybe there is an atomic nucleus where most of the matter is concentrated in the center of the atom, and then the rest of the atom is mostly empty space. Maybe that's where the negative charge was. And this also goes against the plum pudding model, because it's kind of almost equal opposite of this model, right? Because the atom was a center of kind of a loose positive charge. Now Rutherford is saying the atom is mostly a loose negative charge. But then again, Rutherford is also saying we have this supermassive part that's in the center of the atom, and I'm going to call it the nucleus. So that's what he more or less figured out. And then further experimentations, we've found out that the positive charges are called protons, and the atoms are neutral. So the number of negative charged electrons outside the nucleus in the electron cloud, and he didn't use the word electron cloud. I'm jumping ahead to contemporary times, using the quantum mechanical model that we now use for atoms. And then the nucleus is still strongly positively charged. So this has explained most of it. Although Rutherford said that the atoms are mostly empty space, it's not empty space. It's the electron cloud is what occupies most of the, if you want to call it, the space of around the atom. And I'm saying use the space. It's kind of it's a force field. It's how the electron doesn't have that much mass, but it has a negative charge. It has a magnetic and electronic field, and that's usually what interacts with other things with other atoms. I mean, it can also respond via gravity, but that's a very weak force compared to the electromagnetic force, how they interact. And vast majority of the matter is in the nucleus, and we've kind of already covered all of these points. So some fun facts. Atomic nuclei is so dense a single grain of sand would have a mass of 5 million kilogram. This is kind of taken from neutron stars. So pulsars and black holes are neutron stars, and this is about the density of a neutron star, specifically of those pulsar. So it's debatable. We're not entirely sure what's going on in a black hole. So, but we're relatively understanding that it works this way for a pulsar, but because of our current understanding of the laws of physics, we're not entirely sure about black holes and other singularities. So what about their size and mass? Generally speaking, protons and neutrons are about 2,000 times as massive as an electron. Neutrons are slightly more massive. So in the nucleus of an atom, you have positively charged neutrons, and in the nucleus of the atom, there's also something called the nuclear strong force, or also known as the strong force. And the strong force is named such that because it's stronger than the electrostatic force. So generally speaking, unlike particles attract, but like particles repel. So in the nucleus of an atom, you have a bunch of positive charges, and to add more attractiveness to these positive charges, neutrons are also in the nucleus, and the neutrons also have the strong force, but they also do not have a net charge. The particles, protons and neutrons, can be further broken down into smaller particles called quarks. But the net charge of a neutron is 0. The net charge of a proton is 1.6 times 10 to the minus 19 coulombs, a unit of charge. And electrons is the opposite of that, the negative 1.6 times 10 to the minus 19 coulombs. So, and we've already mentioned that. So here shows that unlike charges attract, like charges repel. But if you sum them together, you get 0. So this is the nature of atoms. Atoms are neutrally charged. Later on, we'll talk about ions, and ions are charged atoms, and I have to kind of use the air quotes around atoms because it's an oxymoron to say charged atoms because they mean two different things. So an atom, by definition, is neutral, but by adding or subtracting electrons, it always works that way for ions. Electrons are exchanged. Protons don't change. Protons define the element, which we will learn later. So this chart here shows the relative mass in kilograms of protons, neutrons, and electrons. And the charge is relative. The charge is 1.6 times 10 to the minus 19 coulombs. So we're just giving it just the relative atomic charge of +1 or -1, and the neutron total charge is 0. Neutrons, if set by themselves, will decay into a proton and electron. So neutrons are typically not found free. They can be a product of nuclear reactions, but they typically are very short-lived as far as existing outside of the nucleus of an atom. So an example for this is an electrical storm. So if you look at the sum of charges of the Earth, for instance, it's going to be neutral or thereabouts, but you can get temporary perturbations where charges build up in some area, but then if too much charge builds up, then you can have things like lightning strikes. And with current, it's just kind of strange though. But the way that we describe current flow, like charge flowing, it always goes from positive to negative. And that's how we describe it. That's because Benjamin Franklin, when he was doing this, he had to pick one, and he picked the positive going to the negative. And it's usually, I think he probably picked this because if you've ever played with batteries, the positive terminal is the one that sparks. Like if you're on your car and you put your positive terminal, it's the one that's going to spark. And so Franklin probably thought like, oh, that must be where the charge is going. And it's actually the negative goes to the positive. So the actual charge flows the other way, but we consider current going from positive and negative. So that's one thing you'll see. Although it's one thing about us humans, once we decide something, we almost never change it. So positive charge moving is how we're going to describe current flow from here on out, even though we know it's wrong. So way to go, humans. So elements, we define them by the number of protons. So specifically the number of protons in the nucleus of the atom, and this is also known as the atomic number. And we give the atomic number the symbol Z, and that's just the charge. That's just the charge for in nuclear chemistry. And for instance, helium has 2 protons. It has a atomic number of 2. And aluminum has a number of protons, 13. So the number of protons is what defines an element. And here's a periodic table, and we'll talk more about the periodic table later in this lecture. But to show you from left to right, it is organized in this fashion. It is a weird way to organize things, but we'll go over that in a little bit. Why it's organized, or partially why it's organized this way. It's more accurately described with a quantum mechanical model of the atom. But if you see the numbers left to right, always increase with the number of protons, the atomic number. So hydrogen has 1, helium has 2, and so on. So we usually have symbols based off of the English name of the elements. For instance, C is carbon and bromine is Br. So, but there are some other ones. Quite frequently, we use Greek and Latin names. These are not all that way. I mean, not mention the textbook. W is Wolfram, for instance, and that's German. But there is a hodgepodge of things. So and in different languages as well. I know that natrium it's similar in Hungarian, for instance, for sodium, although we call it sodium. And it's really a hodgepodge of things that we have as far as the way that we name the elements. So here are some examples of the Latin terms for it, and there's more. So gold is aurum, for instance, and you might also see that in Spanish. If you know Spanish, the word for gold is oro. That's similar to Latin aurum, but also that's not true for everything. So for instance, in Spanish, silver is plato, in that, and that's has nothing to do with argentum like that. But although they found a big silver deposit in South America, and they named that area Argentina based off of that huge supply of silver. So there are some naming here from that. And this is not true for all languages. So iron is var, for instance, in Hungarian. And gold is Jing in Chinese, for instance. So there's not really necessarily anything that's similar for all the languages. Although we do have the periodic table in common. We do have that. So Greek is another one. So argon for argos, meaning inactive, and bromos, meaning smelly. So that's because bromine does smell pretty bad. And it's a very pungent smell. All the halogens smell very pungent. Halogens is the name of the group we'll talk about later. So there's also some elements named after countries. There's also some named after people too. So we'll talk about the people in a second. But polonium after Poland, francium after France, and americium. So the way you say that word is americium, from the good old US of A. And we have some named after scientists, like there's, although not a scientist, Nobelium, we have Einsteinium, Seaborgium. Glenn Seaborg was alive when they named the element after himself, but Marie Curie was an amazing scientist, won 2 Nobel Prizes. Her daughter also won a Nobel Prize, so Curie is just an amazing powerhouse of a scientist, an amazing person. So let's go then talk to the periodic table, and you can see that some periodic tables, including in this textbook, have the names of that. So, but the organization, it's still a little strange. You might notice a few things, like now on this one we have a colored for nonmetals, metals, and metalloids, and we will talk about the properties of those in a bit. This is a Russian chemist, Dmitry Mendeleev, and Mendeleev noticed some patterns of elements. And not only did Mendeleev notice patterns of elements, he predicted properties of future elements. So this is actually really amazing, an amazing scientist. And he was mostly right. Glenn Seaborg went and later on revised the periodic table. And this is kind of an argument that's between Russia and the United States. The Russians say, our nation developed the periodic table, and the USA says, we've developed the modern periodic table, saying we've gone beyond Mendelev's work. But I think Mendeleev was absolutely amazing that he was actually able to predict properties of elements not yet discovered. And also, I have to understand, at this time, chemistry was very much influenced by a group of people called the alchemists. Now, alchemy, this was an idea that it was almost a religion, and certain people like Isaac Newton was an alchemist. If you are of pure spirit, you could discover the Philosopher's Stone. Although I know if you know Harry Potter, they say the Sorcerer's Stone. It's actually the Philosopher's Stone, and then that person can create the elixir of life and turn lead into gold. So of course, there is no such thing as a Philosopher's Stone, at least not in a physical sense. You could argue spiritually or certain things, certain activities like exercise and eating well. That's the elixir of life. But as far as the real Philosopher's Stone, that is a physical object that does not exist. And if I am incorrect and it does exist, you may give that to me for an automatic A in the class, no questions asked, of course. So yeah, and of course it's a fictional thing. But Mendeleev was very, very key in the periodic table, and the idea that there are certain properties that elements share. And so looking at these, Mendeleev, instead of just organizing the elements in a straight line by atomic mass, started to organize them in columns, saying certain columns had similar properties. And this is the idea of periodic law. And so remember, law is a summary of observations, and then we will cover this much more in depth later. But let's go on and talk about metals, nonmetals, and metalloids. So metals, as kind of stated, they are very similar. Almost every single metal is kind of silvery in color and shiny. There's a few exceptions. Copper is kind of a red color. Gold is kind of a yellow color. Potassium can have a little bit of a purplish hue, and osmium can have a little bit of a bluish hue, but both of those are because of their oxide. Potassium and osmium, their color with the naked eye is because of their oxide. Bismuth can kind of have an iridescent look to it as well, but that's just the way that the light is hitting it in various angles. So, but pretty much all the metals look just like, kind of dull gray, silvery color. Very similarly, though, they are ductile, meaning they're bendy. They tend to conduct heat and electricity well. Then you have nonmetals that tend to be brittle. They respond by when they form covalent bonds where they share electrons between them. Metals form metallic bonds where there's like a sea of electrons between them. Metals and nonmetals react typically by the metals giving electron density to the nonmetals. And although these are general rules, though, that's one thing, is that when we talk about these are not completely true for every single circumstance forever. So I said that metals conduct heat and electricity very well. Carbon can conduct heat and electricity. Diamonds are very, very good at conducting heat, and also graphite can conduct electricity. So that's not true for everything. Then we have these in between, and you see there's a step ladder here, and we have these things called metalloids, sometimes called semiconductors or sortaconductors. And most of them are still silvery. If you look at them, they still look kind of like silvery, at least in their pure form. And these sortaconductors, well, metals will conduct at pretty much any, like, at least at room temperature, like what we consider room temperature, they conduct just as is. But silicon, for instance, you have sitting at this temperature, it does not conduct. But if you raise the temperature, or if you add a certain potential to the electron, it will conduct, and that is the basis for our silicon logic transistors, transistor logic, has to do with 5 volts being put through a wire and hit on the transistor. At 5 volts, silicon will conduct electricity, whereas sitting there doing nothing, silicon does not conduct electricity, and that is the basis for all our computer program, is that 5-volt gap of silicon. So, mentioned this already. I didn't mention lustrous. Sorry, metals are often lustrous, but they can also, depending on their activity, can tarnish. Even like the alkali metals like lithium, sodium, these are very shiny when they're pure. And generally speaking, they tend to lose electrons when they undergo chemical reactions. Not always true, but usually. And nonmetals are a little varied, but it depends. And you notice with the states of matter at room temperature, it really depends. I mean, that's also true for metals. Metals tend to be solid, but there are a few. Mercury and maybe you could argue cesium are liquids at room temperature. None of them are gaseous at room temperature. But although mercury does have a vapor pressure, so you shouldn't go and sniff mercury liquid because you can inhale the mercury vapors. So, but generally speaking, it varies. I know I keep on giving you, oh, there's a rule for this, and then there's exceptions for things. So it really depends. This is generally true. Nonmetals tend to be insulators rather than conductors, but this is not always true. Carbon, for instance. So nonmetals tend to gain electrons. They don't always gain electrons, but they tend to. And there are some examples of nonmetals. So metalloids, I've mentioned about this before. And silicon is the one that we use primarily in our computer technology right now. And so you can see here we have the main group element, the transition group element. So the reason for this, later on, talking about the quantum mechanical model of the atom, the first two columns are from the s orbitals, and the right 6 columns are from the p orbitals. The transition elements are when you, in the ground state, the d orbitals are prominent. So you see this for the transition elements, and these are less predictable, and the reason is that it's just a little more complicated to predict things. We can predict things very well using mathematics, but periodic law, there's limits to periodic law. Quantum mechanics is a much more powerful model, but even though it's periodic law is not as good as quantum mechanical model of the atom, we still teach it because it is mostly useful. That's then I told you there's some theories that there's limits to the theories. Periodic law doesn't describe everything, but it's still pretty good. So still pretty good. That's the reason why we're still teaching it. And also further on, you have the lanthanides and the actinides, and that fits there after element 57 and 89, lanthanum and actinium. So that's why they're called lanthanides and actinides. So that's actually, the periodic table should be longer, but we take it off and we put it there because it looks prettier, to be honest with you. And it's prettier because it fits closer to the golden ratio. So we humans, we like the golden ratio, and that's similar to the size of the white portion of the screen here. And we've named certain of the groups. So the alkali metals, you can see that hydrogen is kind of taken off of that. Hydrogen sometimes acts like a metal. At least this temperature and pressure, it does not. Although hydrogen is usually considered to be a nonmetal, but in certain circumstances it can act like a metal. But generally speaking, we consider it a nonmetal, although we keep it over there in the alkalis. And then there's alkaline earths to the right, and then halogens and noble gases. So talking about the properties of these, alkali metals are very reactive. They give up an electron very quickly and easily. And these tend to be very soluble, meaning they dissolve in water really well. So alkaline earths metals and alkaline. The word alkaline, that means basic. It means the opposite of acidic. So alkali metals are alkaline, like an alkaline battery kind of thing. They're basic, not acidic. Alkaline earths, they are also basic, not acidic, but they tend to be less soluble. And if you mix certain liquids together and there is alkaline earth metals, frequently they form precipitates. And remember back to the earth, wind, fire model of earth, wind, fire, water idea. So you pour these two liquids together and then a solid comes out that like, oh, you're forming earth, like the element earth. So these metals, they're alkaline, but they also form precipitates, so we're going to call them alkaline earths. That's where the term alkaline earths come from. Halogens is a based off the Greek root word. It means salt forming. So we use the name salt. Salt has two definitions in chemistry. The first definition is a metal and a nonmetal forms a salt, assuming the salt is not a hydroxide or oxide. So that's one of the definitions of the word salt. The other one is the result of an acid-base neutralization reaction, because then the salt is no longer an acid or a base. It is something else. So, for instance, for our own human sense of taste, the alkaline or basic taste is bitter, and the acidic taste for us is sour. And but what does salt taste like? Does salt taste acidic, or does it taste sour or bitter? And the answer is no, it tastes salty. So it's a whole new chemical process. So it's chemically different than acid or a base. And then the last one there, noble gases. Noble is kind of like more British English, and like the nobility, they don't react. They're very stoic. They're like, I am a noble person. This is the happiest day of my life. Like, no, it is the worst day of my life. You will never know because I am a noble. And that's the idea. They're not reactive. So they're noble gases. They're unreactive. Spoiler alert, they can react. Mwah. But they do react. But it's harder to get them to react. So much more difficult. And they tend to be gases, at least at this temperature and pressure. So I mentioned these before, alkali metals. They follow the first column. They tend to be reactive. Alkaline earths are reactive, but they tend to form precipitates. That's where the word earth comes from. Then halogens, they are very reactive and they form salts. And noble gases, they tend to be unreactive. Although they can be reactive. They generally are unreactive. So I mentioned before about ions and atoms. Atoms are neutral, but atoms, when they gain or lose electrons, they are now referred to as ions. So if electrons are taken away from an atom, they become positive ions, and they are referred to as cations. So this is not cations, it's cation. So it's like the cat, like the Felis domesticus, right? So the cat, that cation. Negative ions are called anions, and we usually show them by the element name and then the charge and the superscript to the right of it. So, for instance, magnesium +2 would be a magnesium atom that has 2 electrons stripped away, and oxygen -2, or 2- written this way, it is oxygen with 2 extra electrons. So here's in a reaction, for instance, lithium metal, reactant proceeds to form a lithium +1 ion plus an electron. And so the charges always have to be the same. Lithium atom is atomic number 3, so it has 3 protons and 3 electrons, and then it forms a lithium ion, so it's going to be 2 electrons, 3 protons, and then plus an electron. Still, all the charges add up. But if you look at the lithium +1 ion, it has 2 electrons and 3 protons, thus the overall charge of it is +1. And then look at this for fluorine. Fluorine reacting to turn into fluoride. So the fluorine -1 anion is referred to as fluoride. The same idea, sum up the number of protons and electrons. There are 10 electrons and 9 protons, so the 9 positive charges and 10 negative charges gives it a relative charge of -1. And again, this is -1 relative to the charge of a proton and electron being +1, -1 respectively, or 1.6 times 10 to the -19 coulombs if you want to be precise. So lithium plus is a cation, and the fluoride anion is an anion. So the way that you mention an anion is you take the element base name and then you put in the term IDE. So that has the word fluoride, for fluorine to fluoride. And generally speaking, with the periodic table, we have what are known as valence electrons. So these are the electrons on the outside. And the outside of the electrons, well, the electrons on the outside of the element, the valence electrons, and then those not on the outside are also known as core electrons. But moving from left to right on the periodic table, that shows you the number of valence or outside electrons. And then the best way to predict the charge is the relative location to the noble gases. So given a choice, are electrons close to, so like the alkali metals, they can either lose an electron to become like a noble gas, or they can gain 7 electrons, and it's hard to put 7 negatively charged particles into an electron cloud because the negative charges repel each other. So it's much easier for the alkali metal to lose an electron. And these are general trends. So the electron configurations of noble gases are relatively low energy, and things bond to tend to be like that, like noble gases. So showing here the periodic table, the alkali metals tend to lose an electron. Alkaline earths tend to lose 2. The halogens, fluorine, chlorine, bromine, iodine, they tend to lose an electron. The oxygen family, I'm using the family, I'm going to use group 6A, sometimes referred to as families. Oxygen family tends to gain 2 electrons. Nitrogen and phosphorus tend to gain 3. Carbon actually is pretty versatile. It can go either way. And boron, group 3A, it kind of follows its own rules. Boron doesn't really fit in this at all. So what good would a lecture in chemistry be unless we had rules that have exceptions to the rules, right? So just to make it more interesting, of course. So let's go on and talk about isotopes again. I mentioned earlier with Dalton's atomic theory that all atoms of the same element were exactly the same, and that's wrong. Actually, elements can have the same number of protons, which is true. That's true. The number of protons defines the element, but each of these can have different number of neutrons. And the different numbers of neutrons in the same element, this is known as an isotope. And generally speaking, there's a natural abundance of isotopes, and this is in general fairly consistent across the Earth. And but it varies. There is a little bit of variance. We have noticed a variance of the isotopic concentrations across the Earth, and we've noticed a very big difference between the isotopic nature of the relative isotopic ratio of things like from the moon. So when we went to the moon and collected moon rocks and analyzed them, like, well, some of these are kind of like Earth, some of these are not. So same thing with Mars, although we haven't been to Mars, but we have recovered Martian material from Antarctica, for instance, and we've noticed that it is different. So for instance, neon has relative amounts. It's mostly 90.48% neon 20. It's 9.25% neon 22, and then a smaller amount of neon 21. And also note that the even number, so Even number of nucleons tend to be more stable. So in terms of, especially with neutrons, well, protons, you can't change. If you change the number of protons of an element, you change the element itself. So, but the even numbers of neutrons and protons, we'll talk about radioactivity later, those tend to be more stable. So this was in terms of the nuclear chemistry. The total mass number is the sum of the protons and neutrons. Z is the protons. It's the charge of the nucleus as well. And the isotopes are the difference between the mass number, the total number of protons and neutrons, and then the atomic number, the number of protons. So for chemical symbols, we usually keep it this way: mass number on the top, atomic number on the bottom. Very frequently, unless you're doing nuclear equations, we drop the bottom number Z, because the chemical symbol, from the chemical symbol, you can imply how many protons that nucleon has. So the nucleon is the individual nucleus. So also sometimes we just use a hyphen. So in neon and the periodic table it's capital N lowercase e, and which letter is capital and which letter is lower is important. So capital C, capital O is the molecule carbon monoxide, and capital C, little o is cobalt. These are two very different things. So it is important that you follow which letter is capitalized and which one is not. So you can write the word neon, or you can use capital N, little e, and then with the hyphen 20 that says neon 20. It's similar. That means and that refers to the total mass number, not necessarily the number of neutrons. That's a total mass number. And when you look at the periodic table, there's certain numbers under it, and that is the atomic mass, and that is the weighted average of the terrestrial being Earth average. So generally speaking, that's as consistent as we can find. That we're discovering more and more inconsistencies, and some periodic tables have ranges, but for this class at this level, we're going to try and keep it at as consistent as possible. So for instance, if you look at the fractional amount, remember percent is actually just the decimal times 100. So for chlorine is 75.77% chlorine 35, and the mass of this, you have to look this up in the book, right? In a book. The mass of chlorine 35 is 34.97 AMU, which is atomic mass units. If you must know, the atomic mass unit is based off of carbon 12. So carbon 12 is defined as 12 atomic mass units, and then everything else is more or less massive, depending on the protons and neutrons. They have different masses depending on their environment, and that has to do with the nuclear binding energy, something that we will briefly talk about in nuclear chemistry. But if you're wondering where those numbers come from and why they're slightly different. And then same idea, it's 24.23% chlorine 37 with that mass of 36.97 atomic mass units. What is the average atomic mass? Well, you take the fraction of chlorine 35, which is 0.7577, times the mass of that, 34.97 atomic mass units, plus then the relative abundance of chlorine 37, 0.2423, times 36.97 atomic mass units, and the total is 35.45 atomic mass units. And chlorine, if something has chlorine, it's pretty easy to find in a mass spectrometer, because you'll have this 1 to 3 ratio of two peaks right next to each other. Once you see that, oh, there's a chlorine atom in this in this molecule. You can find it right away. It's kind of fun to be able to see that and figure that out right away. So let's look at another example here. So gallium 69 and gallium 71, and they have the relative abundances this way. So let's do that. Well, you take the percentage and you turn it into a fraction, and then you multiply it by the masses, and then you sum it together and you get 69.72 atomic mass units going down to 4 sig figs. And I'm sure you've heard the term radioactive before. What does radioactive mean? Radioactive means unstable. So in a nucleus, you have a bunch of positive charges, and positive charges like to repel each other. But there's also the nuclear strong force that's between protons and protons, neutrons and neutrons, and protons and neutrons. It's very attractive, but you can get certain circumstances where there's too many positive charges in the nucleus of an atom, and then the atom's nucleus becomes unstable. And we call the unstable isotopes radioactive. And we found that out because they found out they emitted some radio waves, and that's like the least of their concerns. So radio waves are pretty low energy radiation, but there is much more powerful radiation coming from radioactive nuclei, and so that is well, it was originally that the name stuck, right? Once we humans decide something, we don't change it, but that's radioactive. And it can be harmful to living creatures. So it depends on the types of radiation. We will cover this much more in depth in the nuclear chemistry section of this. There are some good uses of radioisotopes. One of them is nuclear medicine, and I've had this done to me. I've had a bone scan with technetium-99. It's a excited nucleus that emits gamma rays and can be used to image where your bones are and look for things. So you can do this and look at, and it's a very powerful tool to image things like bones, for instance. So here's the review. Go over atoms and Dalton's atomic theory, and talked about Rutherford's nuclear model, subatomic particles. So subatomic, sub means less than atomic particles. So that's where the word comes from. And the periodic table, we've mentioned briefly about the periodic table and how we have similar properties, and how the general parts of metals and nonmetals and the importance of the atomic numbers for atoms. Ions and isotopes are also discussed. Here are the learning objectives and the legal stuff.